Hello everyone, today we're going to learn about the element oxygen. Oxygen consists of 8 protons, 8 neutrons, and 8 electrons. Here we have a visual demonstration of what oxygen looks like. And this alongside it is a water molecule, which consists of a combination of hydrogen and oxygen, specifically 2 hydrogen atoms per each oxygen atom in proportion to the molecule as a whole. Here we can label the hydrogens, and this is the oxygen. The hydrogen is more positive and the oxygen is more negative. That's due to the fact that it wants electrons more than the hydrogen wants electrons. And the reason oxygen wants electrons so much is because, like the fluorine, which has just a few valence electrons, and all you need to become a complete set of valence electrons is 8. So as we can see here, zooming in, we can see that oxygen has a total of 2 inner electrons and a total of 6 valence electrons. So 1, 2, 3, 4, 5, 6 valence electrons. Those 6 valence electrons stabilize oxygen, but it still needs 2 more to become a completely stable atom. And what oxygen does is create bonds such as this water molecule in order to become stable. So what oxygen is doing in this molecule is trying to take the hydrogen electrons, because again, hydrogen has 1 electron per each atom, because hydrogen consists of 1 proton and 1 electron. Sometimes it has neutrons, but that doesn't matter for this case because oxygen and other elements that ask for electrons don't necessarily care about the neutrons. Neutrons just change the weight and the net mass energy of the whole atom. So that's a hydrogen atom, and it has 1 proton and 1 electron. Proton and electron. Since again we stated that oxygen wants the electron, so if hydrogen has 1 electron per each atom, then it's going to need 2 atoms of hydrogen to complete its desire for 2 electrons. Here we go. If this is a hydrogen, this is a hydrogen having 1 electron, then there you go. Oxygen is satisfied, which completes this whole diagram of having 1 oxygen, 2 hydrogens to create water. So whenever you see water or you drink water or interact with water, just remember, not only are you made of 65% water, because you are a human being and human beings are made of 65% oxygen and 10% hydrogen, because we need the hydrogen combined with oxygen to make water. Apart from that molecule, oxygen facilitates and functions in many various ways and processes in the body, because oxygen is very important for other processes. The fact that it wants 2 electrons and needs that to combine and react with other things is what makes it very useful in our bodies, because if it didn't react so much like fluorine and other elements that are very electronegative, then it wouldn't be able to do and perform the functions that we need it to in the body, because without reactivity there is no movement, which is why oxygen is so important. Although it's very oxidizing. In fact, the word oxygen comes from the Greek word oxy, meaning acid, and gen, meaning forming, as in Genesis or gene or genetics. Genesis, originating, generation, oxy, oxygen, acid. Oxy means acid. When you say the word oxygen, you're saying the word acid forming. Acid is created through oxygen. Water is an acid because it has oxygen. It's a pH of 7, but it's still considered an acid because of the fact that it has oxygen. Very weak, non-reactive acid, but it can still be made into an acid. In fact, water is involved in the creation of various acids such as sulfuric acid, hydrochloric acid, hydroiodic acid. In the creation of all those various types of acids, water is involved because it has oxygen. Remember, oxygen simply means acid forming. That's what it means. On its own, oxygen is a very, very fast element, which is what makes it a gas at room temperature. In fact, the melting point of oxygen is negative 218.179 degrees Celsius, and its boiling point is negative 182.95 degrees Celsius. So this is its melting point, and this is its boiling point. So it melts and it boils at a very, very low degree as well. So to create liquid oxygen, as seen in this photo, you need to get it at very low temperatures in order to freeze it, because otherwise it would remain a gas at room temperature. We consist of so much oxygen that the majority of our body mass is oxygen. It exists as water in the human body, and we use it to transport and move things around, because without something liquid in our human bodies, we can't transport things fast enough to get there, because if we were pure solid beings, we wouldn't be able to move things quickly, because solids don't move as fast as liquids. liquids do. And we're not made of gas completely, other than the temporary gas that exists in our lungs when we breathe. It's not really a big component of us. As we can see here, oxygen exists, but in the form of water. Carbon exists in the form of fats and lipids and carbohydrates and DNA and other things. Hydrogen also exists in the form of water. It doesn't exist in the form of gas necessarily. Nitrogen also exists in the form of compounds and DNA and other things. Here specifically we have the other compounds: oxygen, carbon, hydrogen, nitrogen, calcium, phosphorus, potassium, sulfur, sodium, chlorine, magnesium, and less than 1% other. All of these things consist of water, proteins, carbohydrates, fats, and minerals. Not many gases. In fact, none of the elements that I named other than oxygen, carbon, hydrogen, and nitrogen are gases. Well, chlorine's a gas, but most of the elements are solids or liquids because they're bonded to other elements that allow them to be in that state. When we really think about it, we're not just human beings on Earth, we are Earth itself, which makes sense when we take into consideration the fact that most of planet Earth consists of oxygen. Not as much as the human body is oxygen in percentage to the whole mass, but a decent amount. 46.6% of the mass of the Earth consists of pure oxygen, at least in the crust. There's a lot of oxygen in the air that's combined as a diatomic molecule, O2. Oxygen needs to remain as O2 because if it doesn't, it's going to be oxidizing everything. Oxygen in its pure elemental state is very dangerous. Why? Because like fluorine, oxygen requires 2 extra electrons to feel stable. If oxygen doesn't have these electrons, it's going to take them from the environment. And in the case of the human body, since we consist of so much oxygen, if some of the oxygen is unstable, it's going to take electrons away from the other elements within our bodies. And some of those elements could affect the DNA and how it works and functions, and that could inevitably cause cancer or other diseases that we don't want. And that's why it's important that oxygen remains a diatomic molecule, because if there are 2 oxygens, each of them share an outer electron and create a covalent bond that allows them to be stable, because if they share the electrons, they don't need to take them away from any other region in the body or any other region on Earth or in space. In space, oxygen could exist as a pure oxygen element because the UV rays from the sun and other parts of space interact with it and separate it and cause it to become an individual element. And since it's in space, it doesn't have other elements to interact with and react with, so it could remain as an oxygen atom by itself, such as like that. Oxygen was finally given its recognition in 1774 by these 2 individuals, Joseph Priestley and Carl William Scheele. They discovered oxygen around the same time period. One of them was born in Germany, Carl William Scheele, and the other one was born in the United Kingdom, which was Joseph Priestley. They both went through individual methods and processes of discovering and isolating oxygen for the purpose of classifying it individually as an element, eventually. On August 1st, 1774, Priestley obtained a colorless gas by heating red mercuric oxide, which is just a fusion of mercury, here's the symbol for mercury, and oxygen, here's the symbol for oxygen. When you heat it up, you are separating the atomic bonds within the pre-existing molecules of mercury and oxygen, and you're getting it to separate. So by adding heat in the form of a flame in a test tube, you separate the mercuric oxide into mercury and oxygen. If you connect that to a tube as you're doing your experiment, so let's say this is a test tube, this is a mercuric oxide, you separate that in a test tube, you extract it, you put that in water underneath a tube, that tube is in water, the bubbles start coming up, and then you collect those bubbles. The bubbles that will result from the reaction of mercuric oxide is oxygen itself, and that's how oxygen was able to be isolated and separated as an individual element. Before, it was either unidentified, it was either ignored, or it was not known that it was a separate individual element. In fact, these individuals, when they separated oxygen, were still hesitant as to whether it was oxygen because they didn't know, or they wanted to confirm and wanted to be sure that the new gas that they were interacting with was in fact a new element, oxygen. Eventually, one of the original discoverers of oxygen, Joseph Priestley, told one of his friends, Antoine Lavoisier, which was a French chemist and scientist who eventually endeavored into the similar experiment of oxygen and its discovery. And he added on further to oxygen that it was in fact a new element. And also he removed the phlogiston theory that his friend Joseph Priestley, ironically the original discoverer of oxygen, Joseph Priestley, supported the phlogiston theory, which was then replaced with the oxidation theory that his friend Antoine Lavoisier came up with because he told him about the oxygen. So he replaced the phlogiston theory, which was a previous belief that there was phlogistons released in the air which kept the air from being breathable or able to keep the air from burning things such as wood or candles. When there was phlogistons in the air was unbreathable and it was unable to burn things such as wood or candles. And what Antoine Lavoisier did was debunk that whole phlogiston theory, which was a theory superseded by his theory. Phlogiston theory was a theory that something was released in the air when things burned that kept things from burning any further. With his theory in place, oxygen was placed there to show that with the addition of oxygen, things started to burn, and things didn't become unbreathable because of phlogistons being released. Things became unbreathable because of oxygen combining with other things in the air, or other things such as other liquids or other solids that eventually decrease the amount of oxygen in the air. And instead of something being released to create the conditions of being unable to breathe, it was actually something being absorbed and prevented from being released that made the conditions unbreathable or uninhabitable for combustion or living things. So the original discoverers of oxygen were not actually the original discoverers of oxygen. We can see here that Carl William Scheele produced oxygen in 1771, but he didn't publish his findings until 1777, which allowed Joseph Priestley to beat him to the punch. Joseph Priestley publishes his findings of oxygen before Carl in 1774, but you know what? The person that discovered oxygen before didn't even know that they discovered oxygen. In fact, they performed an experiment way before them. In around 1608, a Dutch engineer known as Cornelius Drebbel experimented with a compound known as potassium nitrate, which is just a mixture of KNO3. The elements are potassium, which the K stands for, nitrogen, which the N stands for, and oxygen, which the O stands for. As a result, when he experimented with this compound, he was able to extract a gas. He noticed that the potassium nitrate released a gas, but he didn't identify it, which was why he didn't get the credit for discovering oxygen. If he was the one that identified the air as oxygen that came off of the potassium nitrate, then he would have gotten the recognition in 1608, almost 100 years before his other would-be rivals, Carl William Scheele, Joseph Priestley, and also the previously mentioned Antoine Lavoisier, which was the person who gave oxygen its name and its concept meaning acid forming, oxygen meaning acid forming. There are various other facts and functions about the element oxygen. I'm going to give you guys just a brief overview of the element, of what it can do, and how it's used for in everyday life. So, fun fact about oxygen. This is a photo from a YouTuber's thumbnail showing how liquid oxygen is floating, because oxygen, when it's frozen, is paramagnetic, and that makes it float relative to the magnet over here. So oxygen is affected by magnetic fields. So oxygen is used in our everyday life in the form of candles. The reason a candle burns is because there's oxygen in the air. Without oxygen, things can't burn. Something burning is merely the process of oxygen combining at the molecular level with that element itself. It can either be an element combining with oxygen or a group of elements combining with oxygen. Regardless, an exchange of electrons is occurring because the oxygen is taking the electrons and recombining it in a way that it finds most suitable so that it can be the most stable. It does this relative to the stability of the elements that it's combining with. For example, a famous oxide is iron oxide. At least it's a famous oxide that I know. Fe2O3. There's also another type of molecule that's also similar to iron oxide, but is not exactly the molecular formula Fe2O3, but we're going to use this one for the sake of example. So Fe2O3 is iron oxide, which means that there's 2 atoms of iron bonded to 3 atoms of oxygen. By the way, 3 atoms of oxygen by themselves, another fun fact, is O3 is ozone. Remember, ozone. When there is more than 1 atom of oxygen bound to itself, when there is 3 to be precise, that is ozone. The ozone layer protects us from the UV radiation in the sun. So the ozone layer protects us from the ultraviolet radiation that the sun emits. So let's just say that this is the ozone layer. It's even encompassing the word ozone and the molecule formula ozone. Let's say that this is the sun and it's emitting ultraviolet radiation. Ultraviolet light is merely a super high energetic form of light. It's an electromagnetic wave that's highly energetic, and we can't see it with our eyes, but ultraviolet light goes to Earth, but we're shielded from it because of the ozone layer. And ozone consists of 3 atoms of oxygen bound to themselves. So again, ozone. Ozone is very important. Do not use things such as CFCs because they will damage the ozone layer and they will rip a hole in the ozone layer, and then you will get cancer and your future children will die. If not you, your neighbors or people that you love, because they'll get cancer due to the ozone layer in the atmosphere not being at its full capacity and strength. It gets depleted, so don't use things that deplete it. So just a quick review and overview. There are 3 types of oxygen which we briefly covered here. So oxygen, the pure element, O2, which is found in the air, which consists again of 21% of the air around us. Don't spell it like that. And ozone, which is O3. So O, O2, and O3. That is pure oxygen, which we see in liquid form right here. That's oxygen. O2, which is in the air. It's used to burn this candle. By the way, oxygen in the air is also used in manufacturing steel because the oxygen is used to remove other oxygen in the burning process. Oxygen is important to create steel. We live in an ocean of oxygen, which is why all metals are rusty, because they interact with the oxygen. We're living at the bottom of the ocean, and all that oxygen is being pressurized downwards on top of us on all the metals, causing them to oxidize, which is why most metals except gold and other elements that don't react with oxygen immediately are not oxidized. Sodium is not one of them. So oxygen from the air that we breathe, sweet oxygen, that's what we breathe, and that's what we use during cellular respiration. Plants create oxygen for us during photosynthesis. It just happens to be a product. It's not necessarily for us, but we do use it. We take advantage of the process of photosynthesis. Photosynthesis is merely light from the sun interacting with the plants on Earth, causing them to undergo a chemical reaction and combine the carbon in the air and separate the water to create oxygen. When the water is separated, the carbon is combined, and they use that to create a molecule that we classified as sugar, C6H12O6. So sugar is C6H12O6. As you can see, there are 6 atoms of oxygen in each atom or molecule of glucose, and that's important for us. We use that to move, we use that to live. It's apart from the amino acids or proteins that we also combine. The difference between that is that the amino acids and proteins have the element nitrogen, which we will talk about in a later episode, but it does have oxygen as well. But oxygen is important for everything, every living thing, and that's what we use O2 for. And again, the third molecule, O3, is finally ozone. Ozone is very essential for the air. Ozone is like a blanket that protects us from the ultraviolet radiation from the sun. If we were to go as astronauts into space, we would not survive without a spacesuit, because the ultraviolet radiation and all the radiation in general from the sun would obliterate us and give us all forms of cancers and, if not, immediate death. And that's horrific. That's why we need O3. So that concludes our slightly longer video on oxygen, explained in 20 minutes or less. The previous video was a little shorter on fluorine, explained in another 13 minutes. It's a very interesting video, and fluorine is a more reactive element than oxygen. So if you want to check out the properties of fluorine and how reactive it is compared to the element oxygen that I just described today, feel free to check it out. The link is in the description below. Thank you guys so much for watching. I really enjoy making these videos, and I will continue making them until I reach all 118 elements on the periodic table. Thank you guys. Have a good day.